Hey, welcome to Ones and Zeros. My name's Ben, and today we are looking at the first video in a new series, which I have talked about a little bit in some of my other videos and dev blogs. This is the first of the FPGA Basic series, so a series where we're going to start looking at some of the basic concepts and things around FPGAs, starting today with the first episode where we're basically looking at answering the question, what is an FPGA in the first place? We will also be doing another series, which will be starting shortly, where we start to delve into some of the more in-depth stuff with FPGAs. So if you're new to FPGAs, the basic series is the perfect starting point. However, if you've worked with FPGAs a bit before, then some of the stuff that I might talk about you might already know. You might also pick up some interesting tidbits here and there as well, so it might be worth watching. But let's get back to that initial question. So what is an FPGA? So essentially what it stands for is Field Programmable Gate Array, which is a bit of a mouthful, doesn't necessarily make a huge lot of sense initially, and there can be a bit of confusion. I've seen a few different descriptions of them online in different videos, and unfortunately there's only been one video that I came across where what the person was saying actually made sense, although I haven't watched a ton of FPGA videos either. So there does seem to be a little bit of a misconception that they're like a microcontroller, which they can be if they choose to be, but they don't have to be. So essentially what an FPGA is it's a chip that has a whole array of little modules, and each of those modules has a bunch of interconnects in between them, like wires on a circuit board. And essentially you download a file onto the FPGA that reconfigures all of its modules and its wiring to become a physical circuit based on a circuit design that you've developed on the computer. So essentially what we'll be doing in the basic series is we'll be using a language known as Verilog HDL. The HDL stands for Hardware Development Language, and using that to describe to the computer how we want the circuit to work. The computer then sits there, goes through and figures out what it needs to do with the FPGA in order to reconfigure it to become that circuit. And they're quite powerful tools in that you can use them to create everything from very simple sets of logic gates all the way through to full CPUs and microcontrollers with peripherals and things attached to them. They're quite powerful and very, very flexible, but they're also quite different to what you would do when working with a typical microcontroller. So whereas with a microcontroller, you write a set of instructions in a programming language like C or C++, and dump those instructions onto the microcontroller and it goes through and executes those. In FPGA, we're actually designing a circuit. So that's the major difference. We can design a CPU that we can run instructions on, but again, that flexibility of the way the circuit works is up to us. And as a result of that, I find them quite fun to play with. So let's have a bit of a look at what we're going to be working with. So this guy here is a Terasic DE0CV development board. One of a bunch of development boards, FPGA development boards that I've got in my collection. I've got two of these particular boards. You can also get cheaper variants of something like this. I have one of those, which was one of the first ones I messed with, which I got off eBay. The Terasic ones do tend to be a little bit more expensive than the cheap Chinese knockoffs though, so it depends on what your budget is. But basically what this board gives us is the actual FPGA chip itself. We've also got some SD-RAM that we can play with as well to be able to store stuff. As far as simple input and output, we've got our 7-segment displays, so 6 of those. Below that we've got 10 LEDs, 10 switches, 4 little push buttons, bunch of GPIO, which we can use similar to GPIO in microcontrollers, but all of the stuff done with FPGAs is digital. So there's no analog to digital converters or stuff like that, although we can hook them up to the FPGA if we want to. We've also got an SD card slot, PS2 connector for keyboard and mouse, and we've also got a VGA connector that we can use as well. So a fair bit of flexibility in what we've got hooked up to the FPGA that we can play with on the development board. You can also get development boards that basically just have the chip and a bunch of pins that you can connect wires to wire up to different things as well. However, something like this is great for learning FPGAs with, because you do get all the switches and buttons and RAM and all of the additional stuff to be able to play around with and see how it works. The software that we use for programming this one, if we jump to that one, this is Intel's Quartus Prime Lite Edition. So the FPGAs that we're playing with are from Intel. They are Altera Cyclone FPGAs, the ones that I play with typically. In this case, it's a Cyclone V FPGA on this development board. Altera was bought out by Intel, I think, a couple of years ago now. So I've been using Altera FPGAs since before that acquisition happened, and quite like how they work. I'm used to the software. There is other brands of FPGAs that you can get hold of as well. So I can't remember the names off the top of my head. Mine's gone blank just as I went to think of that. But there is different development board solutions and stuff from the various different manufacturers. Just so happens that this is the particular ones that I like working with. So we've got the Lite edition of Quartus Prime. This is free. If you go with the more advanced versions of the Quartus software, there is quite a hefty cost involved with that, unless you're like a uni student or something. But the Lite edition software is perfect for what we want to be doing anyway, and is fairly simple to use once you get used to some of the concepts with FPGAs. So if you're coming from microcontrollers, there will be some stuff that's kind of similar, but some stuff that's quite a bit different as well. So we're just going to create a new project. So a new Quartus Prime project, and we're just going to look at some very basic stuff today. Firstly, kind of getting used to what the FPGA is a little bit better. There's a few things that will help us visualize that a little bit better. Let's just pop a folder in here, and let's just call it FPGA Basics. Select that one, and we're just going to call it Basics Episode 1. We want an empty project. We don't need to add any files to it at this point. Now, one of the benefits to using this particular TeraSic board is it's one of the ones that's supported in here. So rather than selecting a particular FPGA device and having to go through and set up our inputs and outputs and stuff manually, we can actually just go through and select that one from the list. I do also have a D1 SoC board, which is basically an FPGA combined with a couple of ARM Cortex-A cores as well. So it does actually have a couple of CPUs on board. So we'll have a look at that one in the future, as well as a couple of other Cyclone 4 and I think Cyclone 3 boards that I have. We'll have a bit of a play with moving forward as well. We're not going to worry about any of the EDA tool settings at the moment. We just want to do something fairly simple. And it's going to go ahead and get that project set up for us. Now, the other thing that I want to check when this finishes starting up is that we're not using all of my processing cores for compiling. Because if we do, it is likely going to impact. Okay, so only 2 being used. Awesome. If we use all of them, it's likely to affect the stream, which wouldn't be so much fun. So there's one file that's created for us, which we're going to replace, but basically it's just going through and defining some inputs and outputs and stuff. It's a little bit messy, so we're going to have a look at what we're going to replace it with. We've got our project navigator over on the left hand side, which we can switch through different views. We're going to jump to the files view at the moment. We're going to create a new file. Let's go with a Verilog HDL file. And let's get some stuff copied into there. So if you've seen the way I approach STM32 microcontrollers, you'll recognize the fact that I'm going to throw out a whole bunch of stuff that it's set up for us and do a little bit of it manually. So that's all we're going to want in there. Need to put a line after that. There we go, it's turned blue. Wonderful. This file, we're just going to call app1.v. Save that one. Call him app1.v. Pop him in there. And we'll change the name of that module. I'll explain what the module is and all of that sort of stuff in a moment. We're going to find our file that we've just created in here. It's going to be the main file for this project. So we're going to right click it and we're going to go set as top level entity. And then we are going to go through and delete some of the stuff that it has popped in here that we don't need. Because we can do all of our own anyway. We might keep the SDC file, but we'll get rid of these guys. Nice. And then if we jump back to our hierarchy, we can now see our app1 file has become the top of the stack there. So looking at what I was saying before about what an FPGA is and the fact that it's made up of a bunch of different modules, if we jump into our chip planner, so that little button there, and wait for that one to load, it actually gives us an overview of all of the modules inside the FPGA. So essentially we're looking at the insides of the chip right now. Each of these little boxes that we can see here is a specific module. Around the outside we've got a bunch of input and output modules which connect to our GPIO pins. We've got in the corners some PLL modules which allow us to take in clock signals from outside and then manipulate those to a higher or lower frequency, so we can use those to control other parts of the circuit inside the FPGA, or send clocks out of the FPGA to control other stuff if we want to do that. If we zoom in, we can see a little bit more detail of these boxes. So all of these light blue colored ones are what are known as ALMs, or adaptive logic modules. Or each of these blocks contains 8 adaptive logic modules. Is it 8? 2, 4, 6, 8, 10 of them. Okay, so I can't count. So each of these guys, these white boxes with the smaller white boxes in them, is an adaptive logic module. Each one of those is capable of taking in binary bits and doing logic operations on them, whether we're doing ANDs or ORs or combinations of those guys, binary addition or subtraction, all sorts of that sort of stuff we can do in there. They've also got a little bit of memory in the form of registers in them, which we can use to store values. So quite flexible. And then if we bring up our routing details, all of these things that have just popped up here are the potential wiring configurations that we can use in between the various blocks in order to wire up the FPGA. So that's kind of what I was talking about before, when we want to turn those off for the moment because that does get a little bit messy. But we can see some other blocks as well, which are different colors. So we've got these guys, which if we jump into the tooltip, show it, jump out of our layer settings. Let's see if we can get our it's not giving me the one I want. Nope. Okay, so these guys here are Dsp blocks, essentially. So they're designed specifically for doing maths with binary numbers. So inside each of those is some multipliers, so for multiplying binary numbers, as well as some accumulators or adders. So for doing things like FFT, so if you're doing audio signal filtering or things like that, perfect for that sort of thing. Or if you're building a CPU and you have an ALU that needs to be able to do multiplication or addition and subtraction, then using the DSP blocks can be useful for that sort of stuff as well. The stuff the DSP blocks can do can also be done by the adaptive logic modules, but the DSP blocks are more suited to it, which is why they're included in the FPGA. And as we can see, there's a row of those purple ones here, and a couple more rows over here as well. We've also got the green ones, which are basically RAM. And those RAM blocks, each of those guys, I believe it's 10 kilobits that it holds. Those guys can be used as just normal RAM. They can be used as ROM, so you can preload values into them, and they can be read by other parts of the circuit. There's various different ways they can be used, so you can have two different systems connected to the same bit of RAM, both operating at a different clock rate and both able to read and write from it at the same time. So they're really flexible like that, and got a whole bunch of different uses depending on how they're configured. So again, everything on the FPGA is aimed at being incredibly flexible so that it can be suited to whichever particular project you want to throw at it. Now, we don't have to worry too much about the blocks themselves if we don't want to. The software will take care of most of that for us, and the main thing we need to know is how many of them are actually being used. So depending on the complexity of our design and our requirements as far as power usage and performance or use of space on the FPGA, use of resources, will depend on how the software actually goes about using those. But that just gives us an idea of what we're talking about when we talk about a field programmable gate array. It's an array of gates that are programmable by fields that then act as a physical circuit. So helps answer the question of what is an FPGA. We also have a pin planner. So we're looking at a top-down view of the FPGA itself. This is a BGA packaged one. Some of the ones I have, they are LQPF, so they have the pins around the outside of the chip. But if we jump over to this one, we can see the chip, FPGA chip there is basically what we're seeing on the screen here, and we're looking at all of the pins underneath the FPGA. All of the triangle shaped ones are basically power, so VCC and ground of various types. All of the ones with the X that we're seeing here, these guys aren't being used. And then we've got other ones that have been assigned and connected to various things as per the pin legend that we've got on the right hand side of the screen there. So we can go through and see what they're for. Now, because we've selected this particular development board, it's gone through and set up a bunch of the pins for us. So if we scroll down the bottom here, we can see there's a whole bunch of those that have already been set up and given node names so that we can then get access to them. So that's our pin planner, and that basically helps us to be able to configure the inputs and outputs of the FPGA, which brings us to this file that we've created. So in Verilog HDL, we make use of a bunch of different modules. If you've done C++ programming or another programming that's object-oriented, you can almost think of a module like an object that contains a specific set of functionality that can contain other modules inside it, and those can be connected in different ways and wired up in such a way to get a more complex device. The first part of the module in between our parentheses is a bunch of inputs and outputs. So down to here is basically describing all of the I/O for our module, that whole section there. So we've got a bunch of inputs. I've kind of listed them in the first few are the most important, followed by some of the simple ones, followed by some of the more complex ones, but we'll go through what they are anyway. So our first one is our reset, and that is basically used as a reset signal to reset everything within the FPGA. How that's used is determined by us based on how we describe the circuit that we want it to create. And the fact that it's got an N after it, _N, is basically indicative of the fact that it's a low active signal. So a binary 0 or a low signal will actually trigger the reset, whereas it's normally going to be high when we're not resetting effectively. That will make a little bit more sense when we go through and start using it if it's not already. We have a bunch of clock inputs. We do have a, can't remember exactly how fast, it's a 50 megahertz oscillator. It's in the name right in front of me. So we have a 50 megahertz crystal oscillator on the board, which is connected to these 4 inputs. We can feed these into PLLs if we choose to be able to get a higher or lower clock speed for various things. So much like you would set up a clock on a microcontroller to be able to get it to do what you need it to do and run at a particular speed, we use the clocks in an FPGA in exactly the same way. We've got our GPIOs, and you'll notice that these have got 35:0 in the square brackets, which basically indicates that it's an array of 36 individual signals. So each of the GPIOs effectively gives us 36 pins that we can connect, and whereas we've got these guys which are declared as inputs, these guys are declared as in-out, which means that we can use them either as inputs or outputs or both. We've got some inputs which are labeled key, and we've got 4 of those, so 3:0. And they represent the 4 keys that we've got on the board, just where my finger is on the screen there. We've got our LEDs, which are in between our switches and our 7-segment displays. So there's a row of little LEDs just there. We've got our switches, which are just below the LEDs. We've got our 6 7-segment displays. So we can see each of those guys has 7 signals. Each one of them controls an individual segment of the display. We've got the signals for our PS2 ports. Oh, PS2 port, we've only got one of those. Our VGA output, our SD card, and all of the signals that we need to be able to make use of our SDRAM. So that's basically what all of that is. We're just describing to it what inputs and outputs we actually have. Now, because we've got 10 switches and 10 LEDs, we're going to do something fairly simple, and we're going to make it so that if the switch is on, its corresponding LED is going to light up. Is a really nice, easy sort of example of how we go about making this stuff work. So what we're going to do is we're going to tell it we want to assign LED R to SW, like so, which means any of the signals coming in on SW are going to go to LED R. And this is going to work for all 10 of those signals because we've got 10 coming in and 10 going out as shown up here. So 0 through 9 for our LEDs and 0 through 9 for our switches. So it's going to link each one of those up to its corresponding one automatically for us. We're going to click our Start Compilation button up the top here. We'll save that, and it should go through and get that one compiled for us. Now, we'll have a look at how this works, and then we're going to try something a little bit more complex, which is also going to allow us to sort of see what it does as far as our chip planner, as well as sort of seeing how it will actually show us the actual circuit diagram of what it is setting up in the FPGA for us based on our Verilog HDL code. Now, if you've got a really complex project, it can take longer to compile. That is part of it, because it is a bit of a complex thing that it's got to go through and do. And because we've got only half our cores being used on this laptop, it will be a tiny bit slower than it could be normally. Just because we want to keep some of that processing power for the stream to be able to work correctly and do the encoding and stuff that we need there as well. So typically, if I wasn't streaming, I'd have the whole CPU working its butt off during this process. But it's not that much slower with a couple of the cores disabled. I'm not sure that all of the steps here are fully multi-core. We can see a bit of data starting to come up in our flow summary here. It tells us how many pins are currently being used, so we can see we're using 92% of the available I/O pins on the FPGA. We can see how many bits of our memory blocks we're using, so we've got just under 3 megabytes available there, I think, maybe just over, it's around 3 megabytes. No, that's actually bits, so around 3 megabits. How much of our DSP blocks we're using, so not using any of the memory or DSP blocks. And we can see how much logic utilization, so our adaptive logic modules we're actually using, so less than 1% in this case, so hardly using any of the chip whatsoever, simply because we're wiring up some inputs to outputs directly, so not a lot going on there yet. So that's our compilation report. There is a bunch of extra stuff that it will show there, which we're not going to go into at the moment. But we will go back into another tool, which if we go into our tools menu, there's a bunch of them in here. We're going to go into our netlist viewers and our RTL viewer. And this will actually give us a schematic diagram of what it's actually setting up inside the FPGA. So in this case, we can see all of our inputs and our outputs. The ones with an arrow on the right are outputs. These ones are all inputs, and then the ones that have an arrow on both sides are input and output, so they can be used either way. So this one, for example, is the data bus for the SDRAM. So the SDRAM, we need to be able to write data to it and read data from it. So that data bus is going both ways. Same with our GPIOs and our SD card data connections as well, as we can see there. So that's basically that one. We're going to come back and have a look at that one. We've got something a little bit more complex happening. But what we want to do now is actually program our device with this so that we can actually get it working. So when we open up the programmer, it's currently showing us no hardware, which might be because I don't have that USB port turned on at the moment. Let's just close that and reopen it. Go in hardware setup. We've got a USB blaster, so the actual programmer is built into the Terasic development board we're using. So we're just going to select that one, we'll close that. We're going to add a file, go into our output files directly, and we want the SOF file in this instance. We'll look at what the POF file is in a future video. But we're basically adding this one, and we can see that it's brought up our particular FPGA there and shown that that's the one that we're actually going to configure. So we're going to click start on that, and it should fairly quickly go through and get that written to our FPGA. We'll jump over to our camera on full screen, And we can see that our 7-segment displays have changed. So each of these segments requires a binary low signal or a 0 in order for them to turn off, and a 1 signal for them to turn on. So they're inverted, which is why they're all lit up at the moment. But what we're interested in is the LEDs and the switches below those. So if we go through and we turn this switch on, we can see its corresponding LED turn on. Same with if we go with that one there, and that one there, and that one there, then all of those guys turn on. So basically, as we can see from what we've told it to do, it's just wired up those switches to their corresponding LEDs. So let's get something slightly more complex going, just so that we can see a couple of the other bits, and then that's most of what I want to cover in this video. But we'll try a couple of simple things out first up anyway. So we won't save that for the moment. Let's jump back to this one. We'll close our compilation report and jump back to here. So we're going to do something similar with lighting up our LEDs based on what our switches are doing, but we're going to make it a little bit more involved. So what we're going to do is this. So based on whether our rightmost button on the board is being pushed or not will depend on what the LEDs do. So if we're not pushing it, it's going to do the same behavior as we saw before. It'll light up each LED corresponding to whether or not the associated switch is on or off. However, if we push that button down, it's going to invert that. So the switches that are off, their LEDs will light up, and the switches that are on, their LEDs will turn off. This will look similar to C or C++ if you've used this type of thing before. It's almost like an if-then statement. So it's basically saying if key 0, which is our rightmost key on the board, is true, then it's going to do this, so non-inverted from our switches. However, if it's not being pushed, then it's going to do inverted from our switches. So with this one, if we're not pushing the button, it will be supplying a high signal or a binary 1 to the FPGA. If we push it, then it will actually go low, just because of how they're wired up on the board. So similar thing again, we're just going to go through and compile that. Save our changes there. It's going to run through and get this compiled for us, which allows me a moment to have some coffee. Now this is the very basics of what we can actually do with this. In the next video, we'll start to look at some slightly more complicated stuff, dealing with registers and being able to store data and things like that as well. We might, either in that video or the one after it, look at getting the 7-segment displays used a little bit more and show how we can actually get them to provide us with hex values. So if we're storing hexadecimal values in a particular area of memory, we can wire that up to the 7-segment display so that we can actually see what the data is that we've got stored in that register or on a particular bus, things like that. So just wait for that one to finish compiling. And what we'll see when we go into our chip planner and our RTL viewer, we're going to see there is a little bit more usage, simply because we are doing the inversion of that signal from the switches to the LEDs. So it is actually implementing some logic inside the FPGA in order to do that based on whether we're pushing that button or not. We can see though we are only using 6 of our 18,500 adaptive logic modules, so not very much of the chip being used still. It's quite a capable chip on this board. So again, we'll jump into our chip planner and we can see this guy up here if we move away from that, we can see that's slightly darker than the other blue ones, because that's showing us that that is actually being used. And if we zoom in on this, we can see parts of this have turned blue, which are the parts that are actually in use. And the cool thing is, if we click on this now, we can actually see what the circuitry of the adaptive logic module looks like. So this is inside that particular module. On the left-hand side, we've got a bunch of lookup tables, which are used to implement particular logic, so binary logic like ands or ors or nots or exclusive ors, things like that. The lookup tables are complex enough that they can be used, as I mentioned earlier, to be able to do binary arithmetic or logic operations, things like that, that you might do inside a CPU. There's a bunch of different ways that the inputs and outputs for these guys can be wired up. And it's fairly simply just going through and wiring it up to implement the inversion or non-inversion of our LEDs, depending on whether we're pushing a button or not. Over on the right-hand side is the section that is actually used for registers. So we've got 4 single-bit registers in each of the adaptive logic modules. So using 2 adaptive logic modules together, we can actually store an 8-bit byte of data. And that's something that we will be doing in future videos as well, but just wanted to give you a bit of an idea of what those logic modules actually look like on the inside. So when you think of the fact that these are fairly simple circuits, but we've got 18,500 of them on this chip that we can use, not including the Dsp blocks and the memory blocks as well. It's quite a lot of capability inside that. And when we zoom out from that little ALM there to the entire chip, it's tiny compared to that, which is something I find kind of fun. So we'll close our compilation report. The other thing, if we jump back into our RTL viewer, we can see that our schematic has changed a bit. So we've got a demultiplexer here. So it's taking in an input from one of our key inputs here and taking in our switch, and depending on whether our key is pressed or not, it's either going to send through our uninverted or our inverted signal to the output. And again, as we add more logic and complexity to it, the circuit diagram will start to look a lot more like a traditional circuit diagram that you might be used to. But for the moment, we've only got a little bit of simple stuff going on, but that kind of shows you how that tool works. That can be really useful for making sure that the computer has understood what you're talking about with the Verilog HDL and that it is actually going through and implementing it correctly. You can actually go through and have a look at the circuit diagram and go, has it wired things up the way that I thought I described it? Because it might be that you've missed something like an input or an output and it's gone, okay, that section of your code is not relevant, therefore I don't need to create the circuitry for that part. Is something that can be really useful for trying to find bugs and things like that with the Verilog code. So we're just going to open up our programmer again. Again, we're going to go into output files, add our SOF file there, and we're going to pop that on our FPGA. So that's just programming now. Close our programmer. We don't want to save that. Let's jump to our camera. And again, as we had before, depending on which switches we turn on, the corresponding LEDs will light up. But now, based on the additional logic that we put in there, if we now press the button, we can see we get the inverted signal. So the LEDs that were on before have turned off and the ones that were off have turned on. If we release that, it goes back. So, and that is because it is physical hardware that is actually making that happen inside the FPGA. That will happen way quicker than you could possibly press that button. You can get things happening at relatively high speeds inside FPGAs. Depending on how much you want to spend on an FPGA, you can actually get up to quite high clock speeds as far as implementing CPUs and things like that, but it does start to get a little bit expensive. We can do some really quite cool stuff with this one though, so depending on how efficient your design is and things, you can get really good performance out of it. And one of the things that we will be looking at doing quite a bit moving forward is actually integrating FPGAs and microcontrollers to create something that is kind of cool as well, because we get to see both sides of the equation working together. So that will be coming up in future videos. Let's jump back to our Quartus Prime for the moment. There's a couple of bits that we'll have a look at before we go. So let's just assign hex 0, so our rightmost 7-segment display, and we're going to assign 7B and 7 ones after that. So we're effectively assigning a constant to those outputs so that you can sort of see how that works in Verilog. We're telling it how many bits we want to use. So if we go up to hex 0, we can see that's actually got 7 signals. So 6:0, 0 through to 6. So we want to supply it with 7 bits. We're telling it that we're using a binary value. So we could put an X in there if we wanted to go with a hex value. I think it's an X in Verilog, or it might be a H. Can't remember off the top of my head. Followed by a bunch of 1s. So we might even make one of those 0, make the middle one 0, just so that one of the segments of the display will still be on, because again, those are inverted on this board. If we supply a 0, it will turn that segment on. If we supply a 1, it'll turn that segment off. Let's also assign to hex 1, so the next 7-segment display to the left, some of the inputs from our switches. And because we've got 7 segments but 10 switches, we're going to tell it we want to supply it with info from switches 0 through to 6, which will be the 7 switches on the rightmost of the board. So if we jump back over to this guy, and we'll compile that one. So just going back to what I was saying before about using the B to tell it binary, I believe it's a H for hex in Verilog. Get confused in between Verilog and C++ sometimes due to the fact that you use 0x to denote a hex value in C++. So we are up to the fitter section of the compilation. So analysis and synthesis will basically go through, look at the code and turn it into a circuit diagram. The fitter then takes that circuit diagram and figures out how it's going to fit that into the FPGA based on the resources the FPGA has available. Then the assembler will take that and turn that into a section of code like our SOF file that is what actually gets put onto the FPGA, which configures it. And then it will also run some timing analysis on that as well. So if we're using things that are controlled or operate based on particular clocks, the timing analysis will actually allow us to see whether we're actually going to meet the particular clock requirements that we may have set out there, or whether we may potentially run into issues and are trying to run certain parts of the design too fast. Again, still in the using 6 of our ALMs, and not much of the rest of our device at this stage. So still quite simple. We'll go through and program this one. And pop that onto the board. We can see the lights have turned off on the board while it's programming. And we can see that it's now programmed. So let's jump back over to our camera. We can see that we told it we wanted, for the first 7-segment display, so the rightmost one, we wanted all of the segments turned off except for the middle one in that string of digits, which is actually controlling the bottom segment in our 7-segment display, which is why that one's on and the other 6 are off. And then this next digit, which is currently showing a H, is actually being controlled by the 7 switches down here on the right hand side. So there's 7 rightmost switches. So because we've got 3 of those switches currently turned on, we've got 3 of those segments currently turned off, which are the segments those switches are connected to. We turn all of the switches off, all of those segments light up, and then as we turn each of those off in turn, we'll also be turning off each of the segments on the display, and that's separate to the functionality that we put in there with our button where it inverts the LEDs. So the LEDs are doing stuff separately to what the 7-segment display is, even though they're both hooked up to the switches. So again, quite a bit of flexibility in how we go about getting things to work inside the FPGA. So that is what an FPGA is. Hope that makes sense. If you do have any questions or anything like that, feel free to leave them on YouTube or jump onto our subreddit, and you can leave them there too. See how that camera's behaving. It is behaving at the moment. So if you like that, would love it if you follow us on Twitch, like and subscribe on YouTube. Make sure to click the bell to get the notifications. We do also have a subreddit, so r/ones and zeros just over there, which we do put up information about some of the upcoming videos and things like that, as well as when we post a new video, we do pop a link to it on the subreddit as well. So if you've got any questions, feel free to ask them on our subreddit or on YouTube. I'm happy to answer those. We do also have our Gmail address just down there as well, so send questions to there as well if you like. If you want to help the channel grow, we have a Patreon there. We'd love it if you considered giving us a bit of support there. So just reached our first milestone on YouTube of 100 subscribers in just over 2 months, which is pretty cool, especially for kind of niche content. So keep an eye out for our dev blog number 4, which will be out next week, because there will be a bit of a giveaway as a result of meeting that milestone, and we will be giving away bits and pieces as we hit each of our milestones moving forward. So keep an eye out for that devlog, because we will have details there about how you could potentially score yourself some STM32 microcontroller toys, and they will get shipped to wherever you are, as long as there's no issues with shipping to your particular location from Australia. And we do also have a GitHub, which at the moment does just have STM32 microcontroller code there, but we do have a bunch of code for different devices which is available, which we talk about in a bunch of our STM32 videos that are on our YouTube channel. So feel free to check that out. But we also have some of the FPGA stuff that we work on will also be going up onto GitHub. So if you just want to be able to open it up, even if you don't have an FPGA yet, if you just want to open it up and have a bit of a look at it in Quartus, play around with the code a bit, compile it, see what sort of designs it turns into in the RTL viewer, that's a good way to get started as well. As I said earlier in the video, you can get sort of cheaper Chinese knockoff versions of these boards on eBay. Your mileage may vary, but the one that I bought, the very first FPGA development board that I messed with, I think that one is a Cyclone 3 board off the top of my head. Might be a Cyclone 4, but I'm pretty sure it's a Cyclone 3. Although I had to do a little bit more of the pin setup and things like that manually based on the documentation that was supplied, I still managed to get a fully working 16-bit CPU with a 32-bit address bus running on that FPGA with a bunch of peripherals. It had SPI, UART, SD RAM, because there's an SD RAM chip on that board as well. as well as VGA output and a PS2 keyboard connected to it. And you can do all of that sort of stuff, even on a fairly cheap board. But again, I'm not making any recommendations. If you were wanting to get into this stuff, I'd recommend going with one of these boards or another similar board by a more well-known manufacturer, I guess. Not specifically recommending Terasic, but I have 3 of their boards and I love them. So yeah, but again, not making any recommendations. If they want to sponsor me, then they're going to have to pony up. Anyway, I'll stop talking. And again, thank you for watching. Hope you enjoyed. Would love it if you liked and subscribed. And hope to see you next time. Thank you for watching.